Hello, assalamu alaikum. How are you doing today? Well, we already talked about vector spaces and subspaces. Today, I'm going to talk more about subspaces. Then we are going to move to another concept or another idea. It is called linearly independent vectors. Okay. Well, recall here when we talked about subspaces, we said we have a vector space. Here it is. This is a vector space. And we take some of this, put it here in another set, call it S, with the same operations. And the question was, when do we get S, a vector space by itself? And we found we need to do three things. We need to make sure that this S is not empty, or the zero vector belongs to S. 2, we need to make sure that U plus V belongs to S for all U and V in S. And 3, we need KU to be in S for all K in R and U in S. So those three conditions, together with the inherited ones from the mother space, will guarantee that this is a vector space by itself. Okay? Then we said here, easy options or easy subspaces. Number 1, if you take the zero object by itself, this is a subspace. Number 2, if you take S to be the same as B, that is another trivial subspace. 3, if you take one single vector on S, let U belongs to S. You define, let U belongs to the original. Let U belongs to the original vector space. Take S to be span of U. What do we mean by span of U? We mean all scalar multiples of U. Okay? So that is going to be this set, K, U, such that K belongs to R. So it is obvious this is a subspace, because if you take two vectors here and you add them, the result will be in the same form. And if you take a vector here, you multiply it by scalar, you still get it in the same form. And of course, the zero object is here because you can take K0, and in that case, the zero vector is here. Okay? Now we want to make it more interesting. And instead of taking two vectors, I'm going to take here, instead of taking one vector, I'm going to take here two vectors. Let U1, U2 belong to V, and I'm going to take my S to be again span U1, U2. What do we mean by this? We mean if you take the linear combinations, so this is going to be K1, U1 plus K2, U2, such that K1, K2 are real numbers. That is what we mean by span U1, U2. So all linear combinations of this form. Well, you can check the three conditions here. Let's do that quickly. Then after that, we try to think about the geometric meaning of what we are doing here. Well, if you think about it here, take K1, 0, K2, 0, you get the zero object here. Take two elements in S of this form and add them. Then it's obvious that after one step, you are going to get them of the same form, and that means U plus V belongs to S. Take a vector of this form, multiply it by another scalar, you are going to get the result of this form, so that is obviously a subspace. Now, from a geometric point of view, what does that mean when you do this? Well, let's think about your vectors in the plane, like what you used to do in General Physics 1. So here is a vector, and let's say here is another vector. What does it mean here when you multiply this by, this is U1, and this is U2. When you multiply U1 by K1 and U2 by K2, and K1 and K2 are arbitrary in R, what does that mean? It means here you are going to cover all vectors in the plane So any vector in the plane can be written as a linear combination of those two. So basically, those two vectors, they span the whole plane, the whole R2, if you are talking about vectors in R2. Okay, so that is what we mean by span U1, U2. Here, if you want to think about one vector, well, you can think about this is your vector, and now you multiply it by scalar. So what you do, you stretch it or shrink it as much as you want. In that case, you cover all vectors along a line. Look, all vectors along a line, they are covered by span of U. And in that case, think about it. If you add two vectors along a line here, the result will be a vector on this line. Similarly, if you take a vector, multiply it by scalar, it is still on this line. So this is the geometric kind of visualization of what we are doing here. This can be generalized not only for two vectors. In general, you can take n vectors and then take S to be span of those vectors, U1, U2, Un. The result is a subspace of V. Okay? So again here, what do we mean by this? We mean all linear combinations, C1, U1, plus C2, U2, plus Cn, Un, such that C1, C2, Cn are real numbers. Okay? Look here, when we write span, we put commas here. When we write linear combinations, we add them. All right, let's now take specific examples. I'm going to take my vector space to be M22. M22 is my vector space. And I am going to take span of those four matrices. 1, -1, 2, 3, then 0, 2, 1, 4. So here, in this example, I am going to take my vector space is M22, and I am taking here 1, 2, 3 matrices in V. I'm taking the span of that. So this is a subspace. Now the question, is this matrix in this subspace? Okay, so that is what we need to check. How do we check that? Well, we need to see whether we can write this as a linear combination of those three vectors. So let's check that. Can we find C1, C2, and C3 such that C1 multiplied by 4, 0, -2, -2, plus C2 multiplied by 1, -1, 2, 3, plus C3 multiplied by 0, 2, 1, 4 equals 6, -8, -1, -8. That is the question. Well, you have here a system of four equations. And how many unknowns? In 3 unknowns. So what you have here is 4 C1 plus C2 equals 6. Here you have negative C2 plus 2C3 equals negative 8. And you have negative 2C1 plus 2C2 plus C3 equals negative 1. And 3C, no, negative 2C1 plus 3C2 plus 4C3 equals negative 8. 6, negative 8, negative 1, negative 8. Yes. You solve this system using the ideas we had in chapter 1. So here you do the augmented matrix and the row reduced echelon form, and you see what you get. What you get is going to be this matrix. I'm going to skip the details and just write the reduced row echelon form here, since all of you know how to get here. So this is 1, 0, 0, 0. This is 0, 1, 0, 0, 0, 0, 1, 0. And here you have 0, 0, 0, 1. So what do you see here? Obviously, from here, no solution. So it is not possible to find C1, C2, C3 such that this linear combination gives you this. So basically, is this in S? The answer is no. This matrix does not belong to this subspace. Okay? All right, let's take another example. Example 2. I'm going to take my V to be P2, polynomials of degree at most 2. And I am going to take my S to be span of those 4 vectors. 1, minus x plus 2x squared, 3 plus x, 5 minus x plus 4x squared, and negative 2 minus 2x plus 2x squared. 1 minus x plus 2x squared, 3 plus x, 5 minus x plus 4x squared, minus 2 or negative 2 minus 2x plus 2x squared. All right, so this is P1, P2, P3, and this is P4. Now the question is S equal P2? So the span of those 4 vectors, is it going to be all of P2 or just proper subset of P2? So how do we address this question? If this is going to be P2, it means if you take any vector in P2, any vector, let Qx equals ax squared plus bx plus c in P2. Can we find C1, C2, C3, and C4 such that C1, P1 plus C2, P2 plus C3, P3 plus C4, P4 is Q? That is what we need to do. Can you write this arbitrary vector as a linear combination of those 4 vectors? If the answer is yes, then in that case, S is going to be all of P2. Well, let's see. What do we get here? Certainly, we are going to get here linear system that we need to solve. So C1 P1. So let me decipher this and write it as a linear system right away. So we are going to get C1 plus 3C2 plus 5C3 minus 2C4 equals C. And we are going to get negative C1 plus C2 minus C3 minus 2C4 equals the coefficient of x is B. Then we are going to get 2C1 plus, we don't have x squared here, plus 4 C3 plus 2C4 equals A. So here we have 3 equations in 4 unknowns. Again, it's a linear system that you need to solve, and you write the augmented matrix, and you do elementary row operations to get an echelon form. And I jump to the conclusion again here. You are going to get reduced row echelon form. You are going to get 1, 0, 2, 1, 0, 1, 1, negative 1, 0, 0, 0, 0, 0. And now here we are going to get 1/4 C minus 3 over 4 B 1 over 4 C plus 1 over 4 B, and here negative 1 over 2 C plus 3 over 2 B plus A. So here, what are we getting? We are getting a condition that we need to impose here, which is this 0 or not? If this is 0, then yes, you can find a solution. But if this is not 0, you will not be able to find a solution. So basically here, we are not free to choose whatever we want. If, this is what we are getting. We are getting if negative 1 over 2 A plus 3 over 2 B plus, C here, and A here. If this is 0, then Q belongs to S. Otherwise, it is not. And if you look at this condition, you will find you will not be able to cover all polynomials here. So basically, some polynomials in P2 are not generated or will not be generated by the linear combination of those 4 vectors. So the answer to our question now is no. Is S equals P2? The answer is no, because there are some polynomials that cannot be generated from those 4. Okay? All right. Let's now move to talk about another interesting concept, which is the following. When we take vectors here, let's say I am taking R2, and I am taking span of 1, 2, and here negative 2, negative 4. This is my S1. And here I come and take S2 to be span of 1, 2. What is the difference between this and this? Well, obviously there you have 2 vectors, but here you have 1 vector. But think about the span of that. Well, when you take the linear combinations here and you take here the scalar multiples, what are you going to get? Well, what you get here is in fact the same as what you get here, because this vector, you get it from this by multiplying this by -2. -2 times 1, 2, you get -2, -4. So basically, this putting this vector here does not add any flavor to our set. Why? Because this is coming from this. So S1 and S2 here, they are the same. And that motivates us to distinguish between vectors. And here, we need to introduce the concept of linearly independent vectors. Linearly independent vectors. Well, what do we want? We want in our set, none of the vectors can be obtained from the others. So, let S equals, or let, I'm using S there, so let me use here, P equals V1, V2, Vm. Be a subset of a vector space V. I don't want redundancy. I don't want any of those vectors to be generated from the others. So none of those vectors should be written as a linear combination of the others. So it is like here, I want to see the redundant ones, and I don't want them. Okay? Well, how can we write that in a formal way? B is linearly independent if, let me repeat myself, none of those can be written as a linear combination of the others. So it means if I write C1, V1, C2, V2 plus Cn, Vn, and I set it equal 0, it means C1, C2 up to Cn must be 0. Because otherwise, one of them can be written as a linear combination of the others, correct? So here, F implies C1 equals C2 equals Cn, and that is 0. So basically, what I said, it translates into handling this equation. If, when you solve this, you get C1 equals C2 equals Cn equals 0, it means none of those can be written as a linear combination of the others. And in this case, we call it linearly independent. If a set fails to be linearly independent, we call it linearly dependent. So if this condition is not satisfied, we call it linearly dependent. Okay? Linearly independent, linearly dependent. All right, so let's take some examples here. And as usual, I'm going to start by giving you easy examples. One, V is R2. My set, B, is just one vector. Just one vector. Is B linearly independent? Think about it. Or think about this equation. If you multiply C1, V1, and you get 0, what does it mean? It means C1 has to be 0. So yes, obviously this is linearly independent. So B is linearly independent set. It is linearly independent set. 2. Again, V equals R2. V equals R2. and this is B1, this is B2, equals 1, 0, 0, 1. Is B2 linearly independent? Well, here we have two vectors. It is easy to see that right away. So can you get one of them from the other? Can you multiply this by constant and get this one? Obviously, no. So right away, you can say here, B2 is linearly independent set. 3. V equals R3. And here, my B is 1, 0, 0, 0, 1, 0, 0, 0, 1. Is this linearly independent set? Well, here we have 3 vectors, but they are nice vectors here. So can you get one of them as a linear combination of the others? So if I multiply this by C1, this by C2, can I get this one? If I multiply this by C1, this by C2, can I get this one? Or if I multiply this by C1, this by C2, can I get this one? Obviously, no. Okay? If you don't want to think about it in this easy way, all you need here is just to set this. Call this V1, call this V2, call this V3. So here is C1, V1 plus C2, V2 plus C3, V3 equals 0. Has a non-trivial solution. So obviously here, you are going to get C1 equals 0, C2 equals 0, C3 equals 0. Okay? You know those vectors. Here when I talk about 1, 0, 0, 1, this is actually in physics what you used to call I and J. And this I, J, K. The reason we take them, because they are linearly independent. Okay? So what you used to take in physics as I, J, K, those are 3 linearly independent vectors. And you know, in physics, those I and J, they span the plane. And I, J, K, they span the whole space. Correct? So that is something interesting here. We are going to come to this later on, and we are going to call this basis for your vector space. But that is next time. Okay? For the time being, let's just focus on the notion of linear independence. All right, so B here is linearly independent. Is linearly independent set. All right, let me take this example. 4. I'm going to take V to be R4, and I'm going to take B to be this set of vectors. 3, 8, 7, -3, 1, 5, 3, -1, and here 2, -1, 2, 6, and here 4, 2, 6, 4. And again, the question, is this set linearly independent? Is B linearly independent? That is the question. Well, this question is not obvious. It's not like this one or this one or this one here. It is not easy to see that right away. You need to do some computations. So what do you need to do here? Well, you need to multiply this by C1, this by C2, this by C3, this by C4, set it equal 0, and solve for C1, C2, C3, C4, and see what you get. Okay, so let's do that here. Of course, you are going to get a linear system, and you need to write the augmented matrix and the reduced row echelon form and see the solution. All right, so what do we have here? We have 3 C1 plus C2, or let me write one more step here. Let me write all the details, V1, V2, V3, V4. So here we write C1 V1 plus C2, V2 plus C3, V3 plus C4, V4 equals 0. And then we decompose this into a linear system, or if you wish, you can write the augmented matrix right away. Let's do the augmented matrix right away. So here we have 0, 0, 0, 0, and we are going to have 3, 8, 7, negative 3, 1, 5, 3, negative 1. Well, let me see it from here. 2, negative 1, 2, 6, and here 4, 2, 6, 4. And now the reduced row echelon form, that is 1, 0, 0, 1, and here 0, here 0, 1, 0, negative 1, 0, here 0, 0, 1, 1, 0, 0, 0, 0, 0, 0. And you can see now you have a row of zeros here. So what does that mean? It means here you have a free variable. So it means you have a non-trivial solution. So here you have C4 is free, C4 is free, and C3 is negative C4, which is negative T, and then you have C2, and then you have C1. So basically, there is a solution other than the trivial solution. Correct? So what does that mean? It means this is not linearly independent. No, it is linearly dependent. So those vectors are linearly dependent. Okay? One of them can be written as a linear combination of the others. Okay? All right. One more example, and I'll leave it for you to do it as an exercise. I'm going to change the question here, and five. Again, V equals R4, and B is this set. 3, 0, negative 3, 6, 0, 2, 3, 1. Zero, negative 2, negative 2, 0, and negative 2, 1, 2, 1. Is B linearly independent? Set. Well, as we did here, you have to write a system and solve that. Look, after some practice, you are going to develop some skills here. So if you look here at what we did, what did we do here? So here, those vectors, they are coming the coefficient matrix. And we are seeing the reduced row echelon form. If the reduced row echelon form is the identity, then this is going to be linearly independent. So basically, all you need here is to put those 4 vectors in the matrix and see is your matrix invertible or not. Because when the reduced row echelon form is the identity, it means your matrix is invertible, correct? So basically, if those are the columns of your coefficient matrix. So if the coefficient matrix here is invertible, then in that case, those are linearly independent. If it is not invertible, it means those are linearly dependent. Or if you wish, you can use the determinant. So you don't need to do this. You can see this matrix, see the determinant of this matrix. Is the determinant 0 or not? If it is not 0, then your matrix is invertible, and the answer here will be positive. Okay? So basically, after some practice, you can develop some skills that makes things easy for you. I'll leave it for you now to finish it. Do it at home or do it as an exercise. A few remarks. few or some remarks. One, if the zero object belongs to B, then B is linearly. What do you think? Dependent or independent? Linearly dependent. Why is that? So if you have a set of vectors and 0 is one of them, that's it. It is linearly dependent. So 0 here is going to ruin your set. It's going to make it linearly dependent. Why? Well, let's see. B is, let's say here, U1, U2, UK, and here you have 0. Let's check the condition. C1U1 plus C2U2 plus CKUK plus CK plus 1, 0 equals 0. If they are linearly independent, we want those C1, C2 up to CK plus 1 to be zeros. But now, because this is 0, this can be anything. You can take it something other than 0, and in that case, you get 0. So you can take C1 equals C2 equals CK equals 0, but this one is not 0, and in that case, it is not linearly independent. It must be linearly dependent. Okay, so here is the clarification of the proof. Okay, all right, so any set that contains the 0 object is going to be linearly dependent. Another remark here. 2 n R n if in Rn if B has more than n vectors, then B is linearly dependent. Why is that? So let's understand this better. So let's take here R3. And here, take your B to have 4 vectors, for example. Here is 1, here is 2, here is 3, and here is 4. What we are saying here, this set B must be linearly dependent. It cannot be linearly independent. Why is that? 1, 2, 3, 4. Well, if you do as we did here, what are you going to get here? You are going to get the coefficient matrix. When you write this, V1, V2, V3, V4, you are going to get what? You are going to get C1, V1 plus C2, V2 plus C3, V3 plus C4, V4 equals 0. So how many equations do you have and how many unknowns? You are going to have 3 equations, but you are going to have 4 unknowns, correct? This is a homogeneous system. 4 unknowns, 3 equations. So what does that mean? It means you have 3 variables for sure. So if you have 3 variables, what does that mean? It means you are going to find values for C1, C2, C3, C4 other than the trivial solution, correct? So basically, this is linearly independent. Okay, what I said here for 3, you can write it in general, even if you are talking about Rn. Okay, because in your linear system, for sure you are going to have 3 variables, so you will not be able to get only the trivial solution. All right, so here are a few remarks that will help you to answer certain questions quickly. That's all about linear independence. We have now 2 important concepts. We have the span of certain vectors, and we have linear independent vectors. Now, if we combine those together, that will give us something interesting that we will talk about next time. Okay, so you have span of some vectors, and you have how to check whether certain vectors are linearly independent or not. Please do the exercises about this, and we will continue in our next lecture. Thank you.